Everyone, let's start. So it's my pleasure to introduce our speaker for today, Weijie Su. Weijie is an associate professor at the Department of Statistics and Data Science at Wonderland, University of Pennsylvania. And he has worked on really lots of cool stuff. He's got really cool work on many things like high-dimensional statistics, federated learning, differential privacy, machine learning theory, and so on. He has won a lot of awards, including more recently the Peter Gavin Hall IMS Early Career Prize, the CM Early Career Prize in Data Science, Facebook Research Award, Sloan Award in Investor Career. And today he's going to talk about a really cool idea about owner-assisted scoring mechanisms. So I'll let Weijie explain what it means.
Yeah, thank Neha for the invitation and also for the very warm introduction, and especially thank everybody for coming, especially during the fall break. So I would like to take this opportunity to present some of my work and to seek your advice, because here you know more about me in many parts of my own work, especially from the empirical side of peer review and also mechanism design. So which I'm very happy to have this opportunity to learn from you. And since this is SMU, there's no need to motivate the thing. So machine learning is very crowded. So this is the number of submissions to NeurIPS. So this year, the number of submissions exceeded 10,000. And as a result, the burden on peer review is significant. So usually each paper will be reviewed by 3 or 4 reviewers, and but we only got several weeks to do the job. So essentially we need to hire about 10,000 reviewers and ask them to review each review 5 or 6 papers and in several weeks. So it's really challenging. It's a challenging task. And so Neha has a very nice survey about peer review. From that paper, there was a data about what's the percentage of reviewers in NeurIPS who were PhD students. So it was 70% back in NeurIPS 2016. I guess this number could be only higher nowadays. So it's not that easy. And there was a NeurIPS experiment done in 2014. So about 10% of the total submissions were handled by 2 different sets of reviewers. And so this is a portion where they disagree with each other, conditional on that one set say accept, the other will say reject. So roughly speaking, if all these accepted papers were reviewed a second time, about half to 2/3 of the accepted papers would be rejected. So we need to be literally lucky in this game. So lots of people on Twitter complain about peer review in machine learning. And so this year there was even some controversies on the best paper, outstanding paper awards for ICML 2022. So about 2 of the 10 outstanding papers were later found by people to contain some flaws, and which was also part of the peer review process. So this was some data histogram made by this person about ICLR 2020. So roughly speaking, the average rating is perhaps the single most important factor in decision making. If the average rating is higher than some threshold, the paper is more likely to be accepted. But this is not a single threshold, because once you get accepted, you perhaps will aim for higher. You want, for example, aim for a spotlight or oral presentation, even outstanding best paper award. And so I was new to this huge area of peer review, and I get to know this research area by reading lots of papers of Neha, which are super helpful, especially for this survey paper. It's really comprehensive and great. And but I started to think about peer review several years ago, because from my own experience, I often got some good papers accepted, good papers rejected, and the mediocre papers accepted. For my own, it's still okay, but it's hard to explain to my students and collaborators, junior collaborators, what is good research. I often tell my student and junior collaborators, this is a good paper and should be accepted, but it turns out to be rejected later on. And sometimes my students wrote a random paper with his fellow students and got accepted. And then students got less trust, become less trusted in my own research tests. It's hard to explain to my collaborators. So that's why I start to think about what can we do to improve peer review. So for example, I started a poll on Twitter several weeks ago, asking whether you can get helpful information from reviewers and to improve a paper. Most people say yes. But if we ask, do you encounter any reviewers actually know better than you do about your own submissions? Most people will say perhaps not. So this is an example showing that actually the authors actually perhaps know more about our own papers. So if we can elicit some information from the authors, that would be great, right? We can perhaps maybe improve the peer review process. But however, that's not easy because for self-interest, we all have the intention to say good things about our own things. And this is perhaps even a sad story about Boeing 737 MAX, which crashed 2 times in a row in 2018 and 2019. About 300 people died, which is a tragedy. And later, the investigation showed one of the reasons, there are many reasons, of course. One of the reasons was that FAA actually designated Boeing to self-evaluate this new product. So somehow Boeing didn't disclose everything about the product because it's actually, it's a little bit too long. Basically, they make it longer, but I mean, this part is still short. So, so they needed to use their program to adjust the position of the airplane. Okay, and so here we want to model this as a game between the author and the conference organizers. In an abstract way, we consider this again as the owner and the appraiser. Appraiser can be the conference organizers in this case. So this is our setting. So Alice is an author, or she is very rich. She writes many papers to a single conference, or she owns lots of different houses, for example. So Bob is a appraiser or conference organizers want to estimate the true or underlying quality or ratings of paper. So we assume that Alice knows something about the true or underlying ratings of her own papers. So we here assume that she knows something about, means that she does not need to know everything about these numbers. And for Bob only observes the review ratings given by the reviewers, and which are modeled as the true rating plus some noise. And so we assume that Alice does not observe the review ratings until she makes some decision asked by Bob later. But in all the process, Bob does not know the ground truth. Never. He never knows the ground truths are. So the statement of our project is to ask whether Bob can better estimate the ground truth vector R1 to Rn by asking Alice some questions. So by better, we mean that we should at least outperform the raw estimate using the raw review rating Y. Without any input from Alice, perhaps Bob can only do MLE, traditional things in statistics. So then comes 3 questions immediately. First question, how can Bob formulate his question? What kind of question can be asked? Second, once Alice provides her input, how can Bob incorporate this information into estimation? Last, what is Alice's goal? What does Alice want in this game? So certainly, suppose Alice is assumed to know something about the ground truth. So then estimation accuracy alone is not Alice's taste anymore, right? So let's address the 3 questions. So we introduce a concept, very simple concept called knowledge partition, which essentially is a partition of this n-dimensional Euclidean space. So we choose this space because this is a space where the true vector R1 to Rn is from, right? And this is a disjoint partition of the whole space. Since this is a disjoint partition, then the ground truth must be contained at 1 and exactly 1 set Si. Here, M can be infinity. So then Alice must tell Bob that which Si contains her ground truth, whether truthfully or not. Then once suppose the answer is S, then what Bob does is to solve this estimation problem. This is perhaps the simplest way to incorporate this information from Alice. So essentially, we want to find some R in the set claimed by Alice such that this R has the closest distance to the raw observation Y in L2 distance. And essentially, this is a projection. It's to project Y, the raw observation, onto the set claimed by Alice. For Alice, she wants to maximize her utility in the form of an additive summation over all her N papers. For each of her paper, the utility is given by a function U of the final review adjust rating R1 I hat. So of course, the higher, the better. And that's some randomness. So that's why we take excitation to get rid of the randomness. So Alice wants to maximize this utility by reporting any set, whether truthful or not. So that's the setting. Okay, and so there we give some examples of knowledge partitions. And so this is a trivial knowledge partition because it contains only one set. There's no partition essentially. And here we partition this as fine-grained as possible. So each set only contains one single point. And so this is the first orthant. This is the remaining part of the space. And 0 can be, of course, can be replaced by any different threshold. And here we ask what's the norm of your vector. So here we essentially partition the whole space into n different sets. On each set, xi is the largest coordinate. So essentially to ask Alice which is your best paper. So if we take the example, if we treat the United States as the whole world, whole space, and then if we ask, are you in the States? And then it's not informative at all because you are already in the States, right? And if we ask which state are you from, then it's something which town then are you from? This is very fine grained because town is very small usually. And then which state is something between. So this is a trivial, very simple result. Why do we want to have information from Alice? Suppose in the ideal case, it's truthful. She tells the truth. So S really contains R. And also the shape of S is regular. So we assume that S is convex. So in this case, we can always improve estimation compared to using the raw rating. Actually, this is a deterministic result. We can even get rid of the excitation because this is a basic result in convex geometry that if we project onto a convex body, we always reduce the distance between any point on the convex body. And but this is not enough because the inequality will become more and more, the two terms will become more and more different if S, the set, is smaller. The smaller the S is, the better actually we will have Bob better narrow down the search space to find the ground truth. And so this is actually is reflected by this result. So roughly speaking, in these two extremes, if the noise level goes to 0, I will go to infinity. And there are two cones which S2 is smaller, both contain the ground truth, then the risk associated with a smaller set, it will be smaller. Interestingly, I cannot prove in the case where sigma is a fixed level in this case, but I believe this is always true. Okay, so now this is Alice Wonderland ahead of us, although we haven't achieved at this moment. So we hope that Alice will be truthful, and so the ground truth is contained in the set. And meanwhile, all the knowledge elements are as small as possible. So then we can improve estimation as much as we can. Okay, but not easy because we need assumptions to make Alice be truthful. So now we present 3 assumptions, and we will discuss all the assumptions in detail later. But let's try first just present the 3 assumptions first assumption that Alice knows sufficient knowledge about her ground truth, as long as she can determine which element contains her ground truth. So in this case, depending on the knowledge partition, in general, she does not need to know everything about she does not need to know the vector completely in order to determine the thing, right? And second, the noise term C1 to Dn here are assumed to be IID drawn from any probability distribution. And the later IID actually can be replaced by, can be relaxed to exchangeability as long as the joint distribution is invariant on the permutation. So here the probability distribution can be arbitrary. For example, actually this can have the mean is not necessarily 0. So last is the most crucial assumption. By crucial, I mean that we don't aim for to include all applications, because in some application, of course, the utility is unlikely to be a increasing convex function. But this is the assumption we need. And we will motivate this assumption in the next slide. So later we can relax the utility assumption to be non-decomposable and heterogeneous, in the sense that this also depends on the true quality. And but here it's not the increasing marginal, does not violate the law of decreasing marginal in economics, because this is the derivative of U is with respect to the rating instead of quantity. And stay tuned, we will discuss these assumptions later. Please.
L is maximized for utility, right? So
yes.
Convex or concave?
Convex.
Convex.
Yes.
Okay, I assume you're going to get it right.
Yeah. Convex.
Do you need to know the distribution?
Oh no, there's no need. As long as this is they are drawn from the same probability distribution, it's fine. And so here, the convexity assumption basically can be reduced to this slogan: why it's good to have a junk paper with a outstanding paper as compared to 2 posters accepted at a conference. And we have to, perhaps this is true in conference reviewers, because a paper can be accepted as a poster. That's my own experience. While I was a PhD student, I got a poster, sit then in front of my poster in the hallway, and only 2 or 3 random guys pass through me, asking some random questions. So it's the only difference that it's on my resume. That's it. But if you got a spotlight, many people will listen. And if you got oral presentation, you got more minutes to introduce your work. If you have that best papers, and people will tweet it a lot, then it's a big difference. So the gain actually is increasing. And this perhaps also the case for diamond and the very valuable things. Diamond can be scaled in very fine level. And for fancy diamonds, if the rating is higher a bit, then the price will increase a lot, as opposed to a mediocre diamond. Yeah. So now let's present our first result. Our first result is saying that if Alice is always truthful under the 3 assumptions, then the knowledge partition must be formed by pairwise comparisons, meaning that each neighboring elements sets Xi and Sj, if they are neighboring, their boundary must be part of a pairwise comparison hyperplane involving only 2 coordinates, Xi or Xj and Xj. So on the left-hand side, Xi is larger than Xj. On the right-hand side, Xi is smaller. So that's our first main result. And so this means that in order to make Alice truthful, the only kind of question we can ask Alice is to let Alice compare her submissions, whether it's your first paper better than your 5th paper or also. We can ask all these kind of pairwise comparisons. But this is only necessary at this moment. It's not sufficient. So this means that we cannot Alice to say that both of her papers are great. No, you cannot do. You cannot have your cake and eat it too. You have to only pick one of your favorites. Okay, so that's our first main result. And any questions so far?
I don't really understand what you mean by knowledge partition must be something. question asked by Bob, right?
Mhm.
Why does that have to do with
So for example, this can be addressed by this one. If we ask, what's your quality? Suppose Alice knows her ground truth, the vector. If I ask, what's the exact value of your vector? So in this case, it's not formed by pairwise comparisons. But you cannot use pairwise comparisons to locate the exact value of the vector. In this case, Alice will say, all of my papers are rated 10, for example. They're all great. She will not tell you the truth. She will, if she wants to maximize her utility, she will not.
Also, the logic is that the pairwise partition implies else truthful.
No, truthfulness implies pairwise comparison, because this is if Alice is truthful, then pairwise comparison. Its pairwise comparison is necessary at this moment. It's not truthful. And we will get to the sufficiency later on. Hi, Niha.
So yeah, just to understand, so this is assuming that Bob's estimator is the projection estimator.
Yes, yeah.
There, so this leaves open the possibility that there could be other knowledge partitions and other kind of
Exactly.
scoring rules.
Yeah.
Which
Exactly. Yeah. I asked with some mechanism design people, and so usually they always start with using the revelation principle. So everybody will tell the truth, and they will come up a very fancy estimate to ensure that everybody will benefit by telling the truth. But here, our approach is slightly different. We first fix the estimate the first. But of course, this opens lots of possibilities. And I'm thinking about that. If you have any thoughts, let's chat. So let's give some examples. If we ask what's the exact value of R, then no. Then if we ask all the entries of R non-negative, so essentially it's just if all your papers are above the rating, for example, 5, then everybody will say yes, right? So it's because this is also consistent with our previous theorem. This is not going to be given by pairwise comparisons. And what's the norm of R? No, because this involves three coordinates, no, in general. This only involves 2 coordinates, but there's a gap of 10, so no in this case. But if we ask what the largest entry of R, maybe, because this satisfies the necessary condition. But later on, we will show you that for in this case, we have an independent proof showing that actually in this case, Alice will be truthful. So this will be the next slide later on, please.
Yeah, okay, so you convinced me that like Alice, like after the paper submission, should like truthfully respond to Bob's questions. But the question is like, can Alice still rig this through her paper submission? Like I'm thinking like if Alice has like a good paper, then she might like also want to submit a lot of mediocre papers. That way she can keep saying, yeah, my good paper is better than this. Like, does it insist?
Yeah.
Do you have any work on that?
Yeah, that's a great question. So in principle, she can submit millions of junk papers and rate it the better paper, real paper, higher than all the junk papers. So then the review, suppose the reviewers are random, then there are some junk papers actually will be rated very high by the reviewers. And then this will push the real paper up in the rating. It's possible. But this issue can be solved. For example, can make the utility negative if you get a rejection. This actually, for example, is already the case, I believe, in open review. If you use open review, if you got a paper rejected, you submit many junk papers on open review with very embarrassing ratings, and then you will get a very bad image to your community. And I believe nobody will do it. We will discuss this thing at the last part of this talk.
I did follow. So Alice is looking to maximize their utility. It doesn't matter if it's negative or positive. You can always shift everything. Okay. So why does it matter if it's negative or positive? You can always shift things and the problem is still the same. Right?
Here, by shifting, this basically means that on average, a paper will give you 0 utility. But perhaps this is perhaps not the case, because if we got a rejection, you will get, for example, negative utility. You perhaps don't want to, if you could start again, you don't want to submit this rejected paper. Yeah, so let's get some intuition in the case where n is 2. In this case, the truthful knowledge partition can only be this kind of thing. Basically, cut the plane using a 45-degree line passing through the origin. But if instead of asking whether R1 is larger than R2, can we ask what's the exact value of the gap between these two values? So then the corresponding knowledge partitions is a collection of all the 45-degree line passing through, not necessarily passing through the origin. So in this case, in order to maximize her utility, Alice will tell you that the gap is infinity. I submit the best paper in history and the worst paper in history. Why? Because if we want to solve this optimization program, the solution is going to be this. R1 is a half infinity, R2 is negative infinity. Then for generic convex function, it's not a straight line, for example. Then the sum of two numbers is fixed, but if you push the two numbers, one to the left, the other to the right, and then their sum will go to infinity for a generic convex function. Okay, so now we haven't proved any truthful knowledge partition yet. We only get a necessary condition. But meanwhile, in the Alice Wonderland, we want to have a fine-grained knowledge partition, meaning smaller, right? So then the best candidate are just the rankings. Because if you do all the pairwise comparisons, you end up having a ranking. You know which is the best, which is the second best. And this is essentially the building blocks of all possible truthful knowledge partitions. Because by pairwise comparisons, then each element must be a union of several rankings. So the cardinality is no more than n factorial. So any truthful knowledge partition must be generated by ranking. So that's why we first need to start ranking. And actually, this is the best possible candidate because this is already the most fine-grained. Okay, but now this is a key moment for us. We needed to, for example, in this mechanism, Alice is asked to provide a ranking. Once Alice provides a ranking, we solve this very simple optimization program. We want to find the R such that it has the minimum distance to Y in Euclidean distance, but satisfying the constraint in terms of ranking. So this is isotonic regression. So that's why we call it isotonic mechanism. So the good thing that actually this is truthful. So under the three assumptions, especially the convex utility assumption, Alice will be truthful in order to maximize her utility. She will tell you the ranking such that the underlying two ratings will satisfy the constraint. So this is the best, essentially the best question we can get. We can ask Alice if Alice will be truthful. So here, convexity is crucial. If the convexity utility assumption is violated, so we can construct some cases where Alice will not tell you the ground truth ranking. Here, this is a property about isotonic regression. So L2 distance can be replaced by Bregman divergence. The solution is invariant in this case. Okay, and any questions about this slide and any part before? So now let's try to get some intuition. The proof is based on majorization theory and coupling. But the intuition is very simple. Let's start with the intuition informed by the power algorithm for solving isotonic regression. So the power algorithm works as follows. So we plot the observation according to the ranking. If the observations is already in descending order, then we are lucky. This is just our solution. We don't need to adjust anything. But in reality, there must be some increasing subsequences. What we needed to do is to replace each point by their average. And is this done? Not yet, because there's still an increasing subsequence, not decreasing. So we need to replace by their average. We do until everything's done. So this is our solution. So in this thing, we know that by the so this is always mean preserving. Whenever we do average from the Jensen inequality, we know that we always reduce the convex sum. So depending on whether Alice is truthful or not, if Alice is truthful, then we can imagine that there are not many increasing subsequences. So there are not many averaging steps for this algorithm. So the reduction in the convex sum is relatively small. But if Alice tells you the wrong ranking, completely wrong ranking, it's possible that it's the opposite, it's increasing. So in this case, the power algorithm will give you this solution to average everything. So this is the worst possible case for the convex sum. The utility is the least. So in the case that Alice has two papers, which one is super good, the other is a junk paper. So in this case, if Alice is honest, she perhaps will get a overplantation and a rejection. But if Alice lies, then there will be an averaging step, making both papers perhaps accepted, but maybe as posters. So this is a result due to Chenghui Zhang and saying that for isotonic regression, if we fix the total variation, the best and the worst gap is fixed, and then let n and the sigma, the number of submissions and the noise level go to infinity, then basically the isotonic regression has a risk of n to the power 1/3, sigma to the power 4/3. And but using the raw observation, y will give you a risk of n times sigma square. So the gain is large. It's more and more if n is large, right? N is large and the sigma is large too. So now let's. So how large is n in peer review? This talk has been given to some economics departments, econ folks. When I asked this question, what's the largest possible value of papers some individual submit to a single conference in 1 year? And they told me that 5 or 4. But one told me that a low bound of n is 32, which was achieved by Sergey Levin from Berkeley. He submitted 32 papers to iClear 2020. But this is only based on open data, open review data. Most conference the data are not public. So maybe in reality, this number could be only larger. So early this year, Dan Roy tweeted right after submission deadline of NeurIPS that he submitted 135 papers to NeurIPS. And we followed each other. I asked, what is this joke? And he said, no, because he's leading a large undergraduate course. Each student wrote a paper with him. So they submit this paper in a disputed way. But he, of course, is a master node. And they are ranked #1. So Dan is a funny guy. And but later on, so they are the list of most productive author this year, NeurIPS, because other results have come out. So for example, Bernard Schkoft had 13 papers accepted. If Dan Roy really submits 135 papers, so on average, he would have about maybe 20 papers accepted. But I checked, he only got 3 papers accepted. So he was joking, of course. And it was Nihat's idea last year that actually NeurIPS asked all the authors to rank their papers according to their scientific value. So that was an interesting coincidence. So that's why I learned a lot from Nihat about all kinds of things in peer review. And now let's try to do extension. And this part, we have to, in the interest of time, we have to go this part a little bit faster. So suppose Alice is not aware of the true ranking. Well, can we do something? Yes. Suppose ratings are generated by not the additive model and by more sophisticated models in statistics. Can we do it? Yes, we can do it. So suppose there are multiple knowledge partitions available to Bob. Which one to use? There's a way to combine all the power from all the knowledge partitions. And suppose as utility is not additive, we can do in some case. And what if utility depends on the ground truth? Yes, we can do it. And suppose items owned by multiple owners, which is a case for papers. Each paper usually is authored by multiple authors. We can do in some case. And we can also do the case where even nobody knows the true ranking, and we can do it in some case. So we will go over all these parts, but in the interest of time, perhaps we'll go a little bit fast. So first is about other truthful knowledge partitions, essentially to address the issue where Alice only has some partial knowledge about the ranking about her ground truth. So first, there are counterexamples, meaning that the first theorem is only necessary, not sufficient. If n is 1, of course, there is no comparison. In this case, actually, there's no truthful knowledge partition other than the trivial one. When n is larger than 3, there is a counterexample. So this is still given by pairwise comparisons. So S1 is a pairwise is a ranking, is a cone, isotonic cone, and S2 is the remaining part. In this case, suppose the knowledge partition, the true ground truth, the ground truth is technically in S1, but it's really close to the center. Then after adding noise, then basically most likely it will appear in the larger part of the pizza. So in this case, Alice will not tell the truth. She will say that it's in the larger part of the pizza in order to maximize her utility. And it's a little bit sad negative result, because this shows that in general, a pairwise comparison knowledge partition can be not truthful. But we have some positive results. In the case that Alice has multiple items, but they in different categories, such that Alice knows that, for example, iPhone 14 was introduced last month, right? iPhone 14 must be better than iPhone 13. Of course, in this case, it's hard to compare between two different iPhone 14s. So then Alice can provide a coarse ranking. A coarse ranking basically to find a partition of the set 1 to n, such that any coordinates from I1 is larger than any coordinate from I2, so on and so forth. So essentially, but Alice is not required to make any internal pairwise comparisons in each subset. So we can ask Alice, for example, can you give a ranking for your top 5 papers, for example? And we can also ask Alice, what's your top 10% papers, followed by the next top 10%. And you can also give me which half is better than the other half. Yeah, please.
Because of this assumption that Alice can't determine those of the same grade, it might be possible that Alice can't answer this question, right? Like Alice might not know which paper is exactly on the 10% folder.
Yeah. So great question. Actually, we have if we have multiple knowledge partitions, and we can let Alice choose any knowledge partition to work on. Suppose Alice does not know the 10%, but she knows maybe 8%. But a priori, we don't know which is the cut point. Alice can make the decision, right? But we can make Alice to choose any of them to do the job.
So I guess like most fine truthful
Yeah.
setting, you would have a situation where Alice is incentivized to report all the ranking information.
Yes, exactly. Yeah, so this is, for example, if Alice has 3 papers in the course ranking case, we can ask Alice, what's your favorite paper among your 3 papers? And what's your least favorable papers among your 3 papers? So this is the slice of the knowledge partition in the first author. And luckily, Alice will still be truthful in this case. And this addresses the first early on question. If we ask Alice, what's your best paper? So essentially, this can be achieved by using course ranking. N1 is 1, N2 is the remaining part. So Alice will be truthful. And since this is given by convex linear constraint, so by definition, so this must be a convex set. So by convexity, using convexity, we will always improve estimation. And essentially, yeah, exactly, this addresses your question. Suppose there are multiple knowledge partitions. Each is truthful, but we don't know which one we can use. In this case, we can present all of this to Alice. Alice is just required to pick any element, any set from any knowledge partitions. We just give Alice multiple keys. As long as she can open the door, it's fine. So this is the motivation. So it's possible that if we present a knowledge partition, for example, ask her what's the top 10 papers, top 10% papers, maybe Alice doesn't know it exactly, right? But maybe we can ask Alice to give me top 10% papers. If you cannot, you can give me, for example, top 8%. It's fine. So we can ask Alice to give any cross ranking such that P should be not too small, right? If you give me P is 1, then that there's not much information. P should be larger than, let's say, 5. You give me at least 5 subsets. And for the largest subset size, it should be small. You cannot give me a partition, a course ranking such that one set actually occupies the 99% of the papers. So then it's not good. So as long as this is constrained satisfied, you can give me any course ranking. In this case, Alice will still be truthful. So this is joint work with Professor Jianqing Fan and his student Yuling Yan from Princeton. And so basically, we can extend this result to exponential family. So the proof is enabled by a result due to Barlow and Brown a while, many years ago. So basically, this can be transformed to the standard form of isotonic regression. So we can easily, basically, very easy to carry over the original proof to prove that for exponential family, ranking is still truthful. But we have lots of difficulties when we want to prove the optimality of this result. So, but we have to introduce a assumption. So if the knowledge partition is truthful and the boundary is given by hyperplanes, okay, so there's no curvature in the formation of the knowledge partition, then pairwise comparison is still necessary. In this case, ranking is still optimal. We cannot further break down each ranking. And so if we want to stick with, for example, nonlinear boundaries, perhaps this will make it harder for us to do the projection, right? So computational cost will be high. So if we want to have linear boundaries, then ranking is still the best case. So this is to deal with non-separability utility. So here we basically all of our results can be replaced by U, which is a sure convex. So this is a definition of sure convex. So sure convex is an extension of additive convex function. And there are some examples where this is not covered by additive. For example, last year I was submitting my tenure package. My senior colleagues asked me to pick 3 of my so-called best papers. So in this case, my utility in some sense is only depends on the largest 3 coordinates. So this, of course, is not separable. And this is still a sure convex as long as H is convex and non-decreasing. And if we ask you to pick your best paper, then it's even easy. So it's H of X1, the largest coordinate. In this special case, actually, we can prove that Alice will be truthful. Even the convex assumption can be dropped. So this means that if the conference is really interested in picking best paper awards, then the utility even can be non-convex as long as H is increasing. So this actually now let's motivate the thing when we have a paper, the utility depends on the ground truth, for example. So if somebody tells you that you will get a best paper awards, then for most of us, we perhaps will hope that our best paper, really good papers, receive this paper award. Because actually this year, 2 papers out of the 10 outstanding papers that were found on people on Twitter that contains flaws. And some people even wrote a paper on ICAP explaining why this paper is flawed. So it's very embarrassing for the author who received this paper award. Of course, they would be very happy if this is another paper of their group received this paper award. So this means that actually the utility in reality might depend on the ground truth, not only the rating, also the ground truth. So this result basically saying by integration, this means that the utility will be higher if the ground truth is higher. So in this case, there are some examples where the utility satisfies this condition. In this case, Alice will still be truthful. So this is a multiple owner case. And this is an open problem. I only made some very preliminary results and hope to seek your comments more. So suppose Alice, in the case where all the authors write the same set of papers, in this case, special case, okay? Then each person gives a ranking and get an estimate by the assumptive mechanism. Suppose we average over all the solutions from the M authors, then this is going to be a Nash equilibrium. So if all the other authors are truthful in this case, then the remaining author will also be truthful in order to maximize his or her utility. But this is there's still open problems, lots of open problems. Because in reality, okay, in reality, if we are courses, we still will have our own papers, right? I have papers with my other courses. You have your own papers. So in this case, it's not that easy. And because it's possible that some people will rank strategically in order to push some papers up in this game. So it's a really difficult problem for me at this moment. And so here, suppose Alice doesn't know the true ranking, but she knows that one ranking is better than the other in a relative sense. Suppose they all give the same comparison between these kind of fruits, but pi 1 is correct in comparing orange and apple, and pi 2 is not. In this case, Alice will still be truthful. Relative, in the relative sense, she will still pick the one with the correct comparison between orange and apple. So there are other reasons for isotonic mechanism, and let me list some of them. So here, comparison in some sense is necessary because there's a quota for accepted papers. Ultimately, we want to select maybe 20% of all the submission. And in general, conference papers are easier to compare with journal papers. So last time I gave this talk to some stats department, and I got challenged at the early beginning about how can you compare, how do you know the true quality of your papers? I understand because this is because of cultural difference. For journal papers, like in stats journals, it's because the paper usually contain multiple results and also very long. Usually it's hard, yeah, also my experience, it's hard to make a comparison. But for conference papers, usually are shorter, contains a very clear result. Perhaps it's easy, and in terms of, and even if the utility is non-convex, then still, at least in some case, will still be truthful in some case. For example, if we ask her if the utility is only about the best paper, and also most papers are not adversary. Maybe they will not think about maximizing their utility. They just tell the truth. And we can also use the mechanism in a soft way. For example, we can only let the senior area chair know the rating, the adjust rating. Even the area chair that does not know it. So maybe if the gap between the adjust rating and the raw rating is high, there's a huge difference. Maybe senior area chair can let the area chair know that you should spend more time with this submission. Okay, and this might also discourage guest authorship because if somebody still on the authorship knows nothing about this paper, then this will create risk for the other authors. And also, the current system, yeah, needs help. So, and so the question that under lots of conditions, Alice will be a good reviewer of her papers. If we ask her to compare her papers, and she will perhaps be the best reviewer if we ask her to provide a ranking. So let's consider real world application. It looks like fancy, but unfortunately, it's a toy example. So I have friends made several papers to Europe last year. So this is a ranking, and that's the several papers accepted. So my friend told me that he would prefer to have these 3 papers accepted. And however, real world is very complex. If we really want to implement this method in practice, there are lots of considerations, and special thanks to Neha, I got lots of useful suggestions for this. And for example, we should be transparent about decision making, asking, telling the authors that how will this the ranking will be used in making decisions. And the author, for example, should have the degree of freedom, should have the right to either opt in or opt out in this mechanism. And also, we must allow partial rankings, because it's possible that for some papers of different areas, it's really hard to make a comparison. We perhaps also need to introduce randomization in assigning the papers to whom to rank. For example, if we only ask one person to rank the paper, then this person perhaps will have a little bit more power over his or her co-authors, right? So then we can make it random in this sense, in this case, to mitigate this issue. Okay? And okay, maybe we can also do multiple ratings, and also, yeah, there's lots of things we need to do in order to make it real in the future. Hopefully it can make it real. I'm still working hard on this. So this is about utility. So I have several minutes. Let me conclude. So when introduced this thing to my colleagues and students, they also have the impression that the utility look like this. If my rating is lower below 6, then my utility is 0. And if above it, I'm so happy. And further increasing the rating actually does not make things different. So actually, I can very easy to convince my friends that this is not the case, at least when the rating is not that high. When the rating is lower, actually, it's really, really low, the utility is going to be negative. Especially when the results, the reviews will be made public on open review, then everybody will know these results when they search on Google. It's very embarrassing. So this means that submitting many junk papers is not that good because utility overall will be, in this part, will be negative. Okay? But the thing that will be a little bit different when the rating passes some threshold, let's say 8. For some people, they just want to ensure a paper, a submission, a acceptance on their resume. So if the rating is high enough, okay, it doesn't make too much difference. But for some people, it's different. Maybe they want to aim for high impact. So a higher rating will still make a difference. So maybe we can try to do something to make this a reality. For example, this perhaps it's increasingly the case, especially when the number of the total accepted papers is here huge. So this year there are more than 2,700 papers accepted by NeurIPS. So an acceptance at NeurIPS really means little nowadays. And so maybe we can use not only Spotlight oral platform, we can use maybe blogs or other ways for a conference to highlight some of the good papers. Maybe then people will aim high for their for this game. Okay, and also high ratings will be on open review, and they will always carry some good positive impression. People will trust the results more if they see some really high rating in long terms. Okay, and now let me conclude the talk with some rambling source. And actually, it's possible that to extend this framework to other applications because there are other cases where you are the best person to know this thing. For example, if we ask who on the earth knows the potential of all the players of the Manchester City, this was a little bit old. Now Haaland was there, right? So Guardiola perhaps is the best person to ask about the potential about the players of Manchester City because he is a coach. And this is a big market for FIFA to estimate the value for each player. And each summer and winter, they'll be exchanged between different clubs. And of course, if Guardiola can tell the truth, then it will make a difference. This is perhaps also for the car leasing company and other possibilities, including teacher, professors writing multiple recommendation letters for many students, and the parental company with the subsidy companies, and also making medical appointments. So when I make appointments early on for my son, and I tell the truth, how serious it was the illness, and then my son can only get to see the doctor in 1 month or later. So later I suggest by my friends and telling me that to say the story a little bit more serious when we make medical appointments. Then we can see the doctor maybe in 1 or 2 days. But this is not good overall because then in this game, everybody will exaggerate the situation in order to see the doctor as early on. But so maybe we can do some mechanism design thing to make it better. So this is a framework for mechanism design with statistical estimation. So Alice knows the ground truth and generate a observation X from a distribution parameterized by theta. And Bob wants to estimate theta, and but Alice knows some information about the ground truth. Can Bob ask some certain questions in a way that Alice will be truthful? Okay, and maybe we can also add external utility. In this game, the utility is internal because once the estimation is given, then the review rating determines the paper acceptance or rejection. So the utility conference does not need to give additional reward or something. But maybe we can, for example, we can give some cash awards to someone, to the authors. For example, Elon Musk is so rich, he can offer this amount of money to every reviewers who are just asked to give a ranking. So in this case, actually we have a result. If the utility is x squared, in this case, actually we can ask more fine-grained questions about the quality. We can even ask, what's the direction of your true vector? Essentially, we can not only know which one is larger than the other, we can only know the proportion between different submissions in terms of their quality. In this case, this will still be truthful. So this is about something about the mechanical design. I'm still new to it. I'm still learn it by myself. By my impression that the design part is very fancy, but the estimation part is a little bit straightforward. Maybe there's the opportunity that we can incorporate some of the model estimation approaches developed by the last 10 years to mechanical design. So there could be some low-hanging fruits, I believe. Okay, this is my this is reference based on which the talk is based on. So thanks for your time.
Such an informative and interesting talk. There were lots of great questions during the talk, but if there are any other questions, feel free to shout out. I'll ask you one thing, the playing devil's advocate. You said that this might mitigate guest authorship. Maybe it might encourage guest authorship. Like I'll tell you that, hey, I've submitted 5 other papers, but if you make me an author, I'll rank this first.
Oh yeah, I promise that I will rank all my papers first to all my different courses. Yeah, that could be possible. But usually senior people will not do this game. I don't know. Yeah, but yeah. So anyhow, when it comes to multiple author situation, which of course is a norm, is a normal case. The questions or the problem is very challenging at this moment. I'm still working on it, and I hope to have possible collaborations with you.
Questions? Right, if not, let's thank Weijie again. Weijie will be around here for a few minutes. If you want to talk with him, please feel free to do so. Okay, thank you.
Thank you very much.